you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Filippo Girardi, who will tell us about random purification channel made simple. So Filippo graduated in physics from University of Pisa and the Scuola Normale Superiore. His master's thesis, supervised by Giacomo De Palma, is on characterization of quantum neural networks in the large width limit. And then he did his PhD at the University of Amsterdam and QSolve under Ludovico Lamy. And after that, he moved to Pisa, where he is continuing his doctoral studies at SNS. And his current research focuses on quantum Shannon theory, with emphasis on hypothesis testing and communication, and some interests also in quantum learning theory and continuous variable systems. So Filippo, the floor is yours.
Thank you so much for the kind introduction and also for the invitation to give this presentation. So today I'm going to give an overview about this paper, random purification channel made simple. So maybe you already heard about this new technique called the random purification channel that was introduced a few months ago. And our contribution in this paper was to consider this tool and try to make the proof as simple as possible, a completely different strategy which does not make any use of representation theory or advanced tool that could be understood also by a master student with basic quantum information notion. We strongly believe that making the proof as clear and as transparent as possible could be an important conceptual tool to have more insights about this new technique, the random purification channel, and to look for new applications and also to understand more properties. For instance, we are going to extend the class of possible input states. I will tell you later about it, from i.i.d. states to permutational symmetric states. And we also, so the random purification channel was used several times for applications in learning theory. In this paper, we also provide a first instance of application in quantum Shannon theory. So this is a joint work with Francesco Annamele and Ludovico Lamy. Let me start by a quick overview of what happened in the last few months. So the initial paper was this work by Tang, Wright, and Zandri, which discussed this acorn trick. So this acorn trick, I don't think they explained why they call it acorn trick, but I will try to give you later just an intuition of the reason. I try to get informed about it, but I'm not 100% sure. It's just a guess. And the acorn trick is just the core principle beyond the random purification channel that they introduce in this paper. And that was later applied in other works to do fidelity estimation, state tomography, channel tomography. And this is the paper I'm going to focus on, the one in which a few weeks later we introduced the simple proof. Then we also use this simple proof to give an extension of the random purification channel to continuous variable systems, so infinite dimensional case. Then there were also parallel works extending the random purification channel to arbitrary symmetries. There were generalization of these ideas to channel tomography. And in this direction, we also provided an explicit construction of the generalization of the random purification channel to quantum channels. So moving from mixed state to pure state can be seen in this other perspective as moving from quantum channels to their Stein spring dilations. And of course, there were also parallel works in this direction. So as you can see here, I reported the days in which a paper about random purification was posted on the archive. And as you can see, there is a spike of posts around Christmas time. So you can imagine that that was a super intense period for the community working on that new tool. And finally, Christmas break. It was a moment of rest, but very intense and a bit stressful before, but super exciting.
Everyone wanted to finish before Christmas, I guess.
Yeah, more or less. I don't know. Because there were so many ideas starting, and so many, I would say, rather simple ideas, natural ideas. And so people were very excited to deepen these techniques and to look for new applications. So this is what I'm going to present today. So the main focus, as I said, will be on the first of these three papers. We'll also quickly mention the results of the other two. And I'm going to start with a super elementary introduction about pure and mixed state, the purification of a mixed state. It's something that you probably already know. I will just tell to fix the notation that I'm going to use. So I will denote by H a finite dimensional Hilbert space. Psi will be any arbitrary pure state in H, and a rho will denote a mixed state, so a positive semi-definite operator with trace 1. Immediately, we see from the spectral theorem that any positive semi-definite operator, trace 1, can be written as a convex combination of rank 1 projector. So if we imagine having a state preparation device which produces this mixed state rho, we get an equivalent description if we imagine having a state preparation device producing with probability P1, P2, and so on, this corresponding state psi1, psi2, psi-d. So the mixed state can be equivalently represented as a classical uncertainty over pure states. And the two settings are physically indistinguishable because when you perform a measurement, by the very description of measurements in quantum mechanics, you get exactly the same statistics by linearity in these two settings. So another setting in which, apart from classical uncertainty, mixed states are very natural to appear is when you take a bipartite system, AB, which we assume to be in a pure state, PAB. Well, if we consider the local subsystem A, that's in general described by a mixed state. Finally, I will denote by phi quantum channels from Hilbert space HA to Hilbert space HP. Two motivating tasks from learning theory are the following. So imagine you have a state preparation device and a non-state preparation device which produces non-i.i.d copies of an unknown state rho. Well, learning theory aims at designing tests M on these non-i.i.d copies of the state in order to produce a classical description of the state, which could be a tomography of the state or property testing, just to see if the state has a property or not. And similarly, we could try to study channels, non-i.i.d copies of an unknown channel by giving an arbitrary input and then performing a measurement on the final outcome of the channel in order to provide a classical description of the channel. The fact is that some of these measurements are only available, and I mean, you have guarantees and you know their properties, you know that they are effective, only, for instance, when the state here is pure. So purification which should make a bridge between mixed and pure state, could be a useful tool to extend these results from mixed to pure state. And I want to stress the fact that in all these tasks, the i.i.d structure, the fact that we had n i.i.d copies of the same object is crucial, and we are going to emphasize this later. Why it's so important and relevant in the random purification channel. So, as we said, if we have a bipartite system in a pure, described by a pure state, then the local system A in general is a mixed state, and the physical operation to get the mixed state is just a partial trace. So it's legitimate to ignore what happens in Bob's laboratory and just to consider what happens in Alice's laboratory. So this is physically allowed. Purification is a sort of the opposite procedure. So given a mixed state rho A, we want to add an auxiliary system B, and so that the system AB is in a pure state AB, psi AB, which by convenience we denote by ket rho in order to stress that it's a purification of rho. And of course, the property of this psi is that when we reduce to the system A, we get, of course, rho A. And do purifications exist? Yes, there are many. One standard is the following one. It's given by this construction. So given the maximally entangled operator between two copies of A, we call them A and B, unnormalized, we take the square root of the density matrix rho A, and we apply it on this state, and this is a pure state, and it reduces to rho A because if we take the partial trace, then the partial trace will act on the maximally entangled and normalized state, and it will give the identity operator on A and then produce rho A. The question is this operation of purifying a state physical? Is it a channel? And the answer, the quick answer is no. And that's even easy to prove. Indeed, if we assume by contradiction the existence of a universal purification channel, so given any arbitrary mixed state, rho A, sigma A, this channel produces a corresponding purification. It's not necessarily unique. Well, by the action of the channel on these states and by the simple property of linearity, we immediately get that this channel acting on convex superposition, in particular uniform superposition of rho A and sigma A, produces a state which is mixed. So it cannot be pure unless rho is equal to sigma, but by assumption, rho A and sigma A are different. So there is no universal purification channel. So this is the end of the seminar. We we cannot do anything for this, and so that's a pity. No, why the random purification channel was really a conceptual breakthrough in from this perspective, facing this no-go theorem. Well, because here we are assuming that this channel produces, I would say, deterministic purification. So whenever I I choose as input rho A, lambda tilde will always give the same purification for rho A. and the same purification for sigma A. So let's move now to the notion of random purification channel to overcome this problem. I will give the formulation. So that's not the original. It's not the first time it was presented, but I will go the formulation that we introduced in this paper, and then I will try to discuss also the reason why in the original paper they called this an instance of the acorn trick. And then I will discuss some recent applications and also generalization of this purification channel by also mentioning this second work, which is a joint work also with Senrui Chen and Marco Fanizza. So probably you're already familiar with the R measure. In particular, here we are considering the R measure on the unitary group. Let me just define the notation I will use. Well, this is the unique probability measure, which is both the left and right invariant over the unitary group. This means that whenever we consider the integral of f, which is supposed to be an integrable function, the unitary group with respect to this probability measure, we have the property that if we multiply on the left or on the right by a fixed unitary and arbitrary unitary matrix, then the result is invariant. This means that this is a sort of uniform probability distribution over the unitary group. And we denote by U this expectation value over uniformly random sampled U. So this is the statement of the random purification channel made simple. It doesn't look simple at all. If you look at it, it is full of definition and complicated notation. Well, I will try to show you that no, it is simple. Let's just ignore all the preliminaries and just focus on the central result. So lambda n is channel, so a physical operation that we can implement in a lab, which acts on rho A tensor n by producing a purification, a given purification of rho on AB, non-i.i.d copies of this same purification, and then a convex combination of purification, of this purification with the action of a unitary, of the same unitary on all the n systems, just on the B party, so not the original A party. Let me give you a pictorial intuition. So first of all, as we said, a mixed state, an arbitrary mixed state, tau, in particular here we have a uniform combination of three pure states, three rank 1 projectors, can be equivalently described as a probability distribution over pure states. So if I produce with probability 1/3 tau1, 1/3 tau2, and 1/3 tau3, then this is physically indistinguishable from having the mixed state tau. Now here we don't have a uniform distribution on a discrete set, but on a continuous set of unitary operators. So how can we describe it pictorially given this state and applying this channel? We get a fixed purification of rho on all the n copies of AB, and then with some uniform probability on this continuous set, we take a unitary, non-unitary, which acts only on the system V. And so it maps a purification, or this purification of rho into another purification. It's still a purification. Again, by representing here the n system, non-i.i.d systems, the channel produces a consistent unknown system B, consistent over all the copies, such that whenever we take these two systems together, we get a purification of rho A. Okay, now that we have the intuition, if you have any question, please feel free to stop me at any time. We can discuss more in detail the structure and the definition, the mathematical definition of these channels. So we define this operator Rn acting on the bipartite system HA-HB, where the two Hilbert spaces are isomorphic, and R is defined for any fixed integer n larger than 1. Given this unusual definition, one can define the channel lambda n the following way by this Krauss form, where first we append the identity on the system B, and then we act with Rn on the bipartite system. This operator Rn is defined as the expectation value of this quantity, where gamma, as I said before, is the maximally entangled unnormalized state over AB. UB is this random unitary according to the R measure. A property of the operator Rn that I'm going to prove later, it's a technical property, is that given any arbitrary rho A state in HA, Rn commutes with non-i.i.d copies of rho A, and here I'm assuming that the system B I have just an identity operator. So I'm going to prove this lemma later. Let's see why it is relevant for the proof of the main theorem. So the fact that this channel is indeed the random purification channel has that property that I described before. So let's just consider the action of this channel on a state rho A tensor n. I can simply rewrite rho A tensor n as the product of two square roots. Now I'm using the lemma here to say that I can commute rho A and Rn. Therefore, I can get again Rn, sandwiched with two square roots of rho A tensor n. And finally, by the very definition of Rn, I get, and by linearity, of course, of the expectation value, I get this expression where the square root of rho A entered the expectation value. And here you can see that quantity appearing in the middle is just a standard purification of rho A, and therefore this is the expression that we claimed above in the statement of the theorem. So the only missing ingredient to complete this proof is just to prove the technical lemma. Well, of course, one should verify that this is indeed a channel, so it's completely positive because it has a Krauss form. It's trace preserving. That's very easy to prove by using the properties of Rn. I will not prove it here, but it's very straightforward. So let's move to the technical lemma, which is the tricky part. The first step to prove the lemma is to show that Rn commutes with all the operators of the form unitary, non-i.i.d copies of a unitary, a fixed unitary on A, tensor identity on B. How to do that? Well, let's consider the action of the unitary on Rn. By the definition of Rn, I can move the unitary here inside. We know that the maximally entangled state allows for the so-called transpose trick, so we can move the unitary to the system V, so by considering a transpose in the basis of the maximally entangled state. Therefore, by writing variance of the power measure, we can redefine W multiplied by U transpose as W prime on B, and therefore this is equivalent to the definition of Rn. It's exactly the definition of Rn, and therefore you see the action of U leaves Rn the same, and therefore they commute. Second step is to consider arbitrary permission operator H in a single system of the Hilbert space, define Hj as the action of this Hermitian operator on the site J and being the identity otherwise. Well, if we sum over all sites this operator Hj, then we get another operator which commutes with Rn. How do we show that? Well, e to the power of I h tensor n is a unitary operator on like you here, and therefore by step one here the two quantities commute for any arbitrary t in R, and so if we take the derivative in zero, linearity it will still commute. But you see here by taking the derivative we exactly get what we wanted. So the fact that this operator commutes. So step two is completed. Now, how do we conclude? Step three, which is the statement of the lemma. Well, consider Rn and the exponential of the sum of these emission operators. If you expand this exponential in Taylor expansion, then you get powers of this sum of Hj. But of course, since this sum commutes with Rn also, the powers of this quantity commute with Rn, and therefore this is equal to 0. But we can equivalently write this exponential as non-i.i.d copies of the exponential of h on the single system, and therefore any strictly positive definite state can be, up to a normalization, can be written in this form. And so we have the statement of the lemma for all rho A of this form, and then by continuity we can extend it to any rho A positive semi-definite. So this concludes the proof of the statement of the random purification channel, the construction, the simple construction. And as you can see, we haven't used any representation theory, which is an important property of this proof, because in the original paper, the authors used advanced tools also to study the circuit and the complexity to implement this random purification channel, but using a lot of representation theory, while here just to provide the mathematical properties and intuition, and we will see also some further properties. There's no need to use representation theory. Any questions so far? Is everything clear? Okay, let me.
I think there's a question.
Yeah.
Sorry, I pressed the wrong button.
Okay. So I will move now to the.
Okay, I guess it's fine. I just have a question out of curiosity.
Yes,
What's the adjoint of this channel? I guess one can just work it out, right?
Yeah. No, but it's you see the form, you can immediately see it's itself somehow, apart from here, but from this. Yeah, but it's very simple to write it, because if you have a Krauss form, then you have to move it to the other side, and then
I see.
And here you will get a trace on B.
Yeah. Okay, yeah.
And you see. So yes, this is Well, it's a deep question. It seems just out of a curiosity, but it's really a deep question what you're asking. Because when we think about applications, so usually you take the random purification channel, non-i.i.d copies, you produce the random purification of that i.i.d state, and then you want to do a test on this state. Now I will discuss more in detail which kind of test one could be interested in. So the adjoint, since we described the probability of an outcome of that test as a trace of random purification applied on the channel, and then we multiply by the test, the metric test. So the adjoint could describe the effective test that we apply on rho A tensor n, no? Because you move the random purification channel to the test by the adjoint, and so you get an effective test to apply without necessary implementation. So this question is it's not just out of a curiosity. It's more. So it's really interesting that you ask. Okay, let me give you an official interpretation of the choice of the word acorn trick for this technique that they use this idea that they used to introduce the random purification channel in the original paper. Yeah. So imagine being in a oak tree forest in autumn. Well, not every year you can see many acorns on the trees, but there are some years in which these oak trees produces a huge quantity of acorns. And during these years, there are many predators, which, well, in general, every year, there are many predators who are looking forward to collecting these acorns for the winter. And there is a certain moment of the autumn where all the trees, in a synchronized way, make the huge amount of quantity of acorn fall in a way that the predators will not be able to eat all of them. And therefore, with the leftovers, for the oak tree, it will be possible to have new trees, no? The acorns will be left, and therefore will produce new oak trees. So why? What is the connection with quantum theory? Well, suppose you have an efficient learning algorithm for pure states that you want to feed indeed with non-i.i.d copies of a non-pure state in order to produce a classical description of the unknown state, like tomography or just testing a property. Imagine you want to apply n copies of the random purification channel independently. So you apply to the first row A and you get a random purification of row A, which is row 1, get row 1. Then you apply it again and you get a random purification, get row 2, and so on. In the end, you will end up with an independent random purification. But this is not an i.i.d pure state. This is not at all an i.i.d pure state, so we have no guarantees on the performance on this efficient learning algorithm for pure states, and so in principle we cannot apply it. So acorn trick, like the acorns do, they fall all at the same time. Well, here we want our state to be purified all at the same time, so all with the same unitary acting on the system B. So here we get, you see, as the action of the random purification channel, consistent over all the copies, random purification. So UB is not known, is still unknown, but we know that UB is the same all over the n copies. And this means that we can indeed perform, it's legitimate to perform this algorithm for learning pure state. And in the end, we will get classical description. After the first step purification, random purification, we get these non-i.i.d copies. We produce the estimation of rho tilde AB, and then we trace out B in the classical description, and we get an estimation of rho A. And this was applied, for instance, in this seminal paper, in which mixed state tomography was reduced to pure state tomography, which was considered to be a completely different case and a simple case. But here they show that one can reduce to the other, and that way they can produce, they can describe an algorithm with a sample complexity which is optimal in all the parameters simultaneously. And this idea was also applied to channel tomography by giving this achievability protocol, which is optimal in the input dimension, output dimension, Choi rank, still not optimal in the time on distance error, but another breakthrough in this field by using this tool. And I just want to mention also this, which was the first application of the random purification channel to operational task, which was the fidelity estimation. So I will just give you a quick idea of, because now the settings in which it was applied are mainly in learning theory, and I did not report it, but there is a very recent paper also in learning theory, which connects hardness of learning with hardness of cloning a quantum state. And this uses the random purification channel as a key tool. So there are new applications, but mostly related to learning theory. So in our paper, we give another application in a different field, which is quantum Shannon theory, and in particular, give an extremely simple one-line proof of a recently established theorem, Uhlmann theorem generalized to quantum divergences. So let me just recall the setting. I will not give you all the technical details, you can find them on the paper, but just an intuition on about how this tool can be helpful in Shannon theory. So the fidelity between two mixed states is just defined this way as a measure of similarity, which is 0 if they have orthogonal support, and it's 1 if the two states are the same. For pure state, it's maybe even more clear. The meaning is just the squared overlap of the two states. And an important variational characterization of the fidelity of mixed states in terms of their purification is given by the famous Uhlmann theorem. So how does it work? Take the two states rho and sigma, fix any arbitrary purification of rho, then the fidelity between rho and sigma is the largest overlap between the purification, the fixed purification of rho, and all the possible purifications of sigma. And this statement was generalized to the setting of arbitrary quantum divergences. So I will explain you later what this identity means in these two papers. And well, it's a highly non-trivial result, which requires many pages of work. And the surprising fact is that if we know about the random purification channel, we can provide a immediate flash proof in just one single line. And I will show you why. So if you are working in quantum channel theory, you are of course already familiar with quantum divergence. let me just, in case you not work in this field, let me just give you a quick overview. So in classical Shannon theory, a fundamental measure of distinguishability between two probability distribution, P and Q, is given by the Kullback-Leibler divergence, defined this way, or called also relative entropy. Generalizing this to the quantum case is not immediate because there could be many generalizations to the quantum case which would give, for classical distribution, this quantity, but the most relevant one, operationally speaking, is the Umegaki, the so-called Umegaki relative entropy, introduced in 1962, which was then proved by Hi and Petz to have an operational interpretation in hypothesis testing. Is defined this way as possible generalization of these expectation value over P of the logarithm of the ratios of the two probability distributions. And a key property of this distinguishability measured between rho and sigma is the so-called data processing inequality. So whenever we perform a physical transformation, the same physical transformation on rho and sigma, they are it's more difficult to distinguish them. They get more and more similar. So if you have to test whether an unknown state is either rho or sigma, and you make any pre-processing, well, in general, this pre-processing will make them less and less distinguishable. So the way to generalize this intuition of distinguishability measure is to say that a generic quantum divergence is a function of the two states which satisfies data processing inequality. Another relevant property that quantum relative entropy satisfies is the weak concavity. So the quantum relative entropy is jointly convex in the two arguments, but it's not concave. If we take a convex combination on the first argument, we get, okay, a lower bound in terms of the convex combination even here, but there is an additive term, which depends on the probability distribution. So that's why we say that it's not concave, but weakly concave. Many useful divergences are not necessarily weakly concave, but they have this property that we call weak quasi-concavity, which is even weaker than weak concavity. So given any finite ensemble of states, on non-i.i.d copies of the state, the space, and any sigma, we ask that the divergence computed in this convex combination is lower bounded by the minimum value that this divergence can take on the support of this convex combination, so on this ensemble, up to an additive term, which is a logarithm of a polynomial of the number of items in the convex combination, so in the ensemble, and the size of the spectrum of sigma. And it just depends, there's an arbitrary dependence on the dimension of the single copy Hilbert space, not n copies, but the single copy Hilbert space. So S sigma, I didn't write it here, but it's just the cardinality of the spectrum of sigma. And many relevant divergences satisfy this weak quasi-concavity. So what is the Uhlmann theorem for divergences? Let D be a divergence, so D must satisfy data processing inequality, and we ask that it also obeys weak quasi-concavity. Then, if we take two states, rho A and sigma A, and we fix an arbitrary purification psi bar of rho A, then we have this identity. So what is the first term, the left-hand side, is just the regularization of the divergence, meaning that we take the limit of the divergence of i.i.d copies of the two states, and then we normalize it. Usually divergences it's not always the case. But some of them are additive. For instance, the omega k relative entropy is additive. So here we don't need this infinity. We just get the omega k relative entropy. Well, this is equal to, remember the Uhlmann theorem for fidelity. We have an extension, a purification here of rho B. And then we have to maximize. Here we minimize because first we had a measure of similarities of distinguishability. Here we have a minimization over all the extensions of sigma. So this is the regularization of the optimization over the states sigma an bn, which reduces to sigma a tensor n on the system A. Without entering into all the steps of the proof, of the one-line proof, let me just mention the key ingredients to show you that it's very elementary. So the first two inequalities here in the proof are just data processing inequality. So the very definition of quantum divergence. Here we use weak quasi-concavity, a special form for this expectation value is just that ingredient. And finally, we use the left invariance of the R measure in order to complete the proof. And you see here this term we are using is random purification channel. Okay, this is just a quick overview of the ingredients for the proof of this theorem in one line. You can check out the paper if you want to know more about it. Let me just conclude by briefly mentioning some applications. So random purification and symmetries. In the original paper where the random purification was introduced, the case considered as an input for the random purification were just i.i.d. copies of a fixed state rho A. Here we show that with our construction, it's easy to prove that also for permutationally invariant state rho AN, the random purification channel has an interesting action. It produces a random purification of a random purification of this permutationally invariant state, which is permutationally invariant. What about continuous variable systems? Well, for instance, take the subset, the special set of Gaussian states, which are sort of quantum generalization of Gaussian distribution, where if rho A is a Gaussian state, not all the purification of rho A are Gaussian states. So if we want to apply a protocol on a pure Gaussian state in order to describe the properties of the original state rho A, well, a naive generalization of the random purification channel would not give necessarily a suitable state for this test. So we identify a subclass of Gaussian states, which are called passive Gaussian states, for which it's possible to construct a random purification channel which preserves Gaussianity. So the output will be non-i.i.d. copies of the same random Gaussian purification. And this was also generalized to arbitrary symmetries in a parallel work by Michael Walter and Freek Witteveen. Particularly interesting also with application to fermionic system, not only to bosonic system. And let me conclude by saying how this generalizes to channels by recalling Steinspiegel representation and introducing the random Steinspiegel superchannel. So if the purification is an extension of the system such that the global state is pure, given a quantum channel from A to B, which maps rho A in phi rho A of rho A, well, a Steinspiegel dilation is an extension of the system to with an auxiliary Hilbert space E and isometry such that rho A is mapped by this isometry to a state tau BE on the global system V, which has the marginal on V given exactly by the channel applied to the rho area. So the natural question is, can n queries of arbitrary quantum channel from A to B can be transformed by a random Stein spring isometry, as similarly to what happens with the purification channel? And the answer is yes. Consider n queries of a channel phi. We want to transform it into a query of a isometry V, a Stein spring isometry V of the channel phi. So we need a auxiliary system E. So let's consider these two Hilbert spaces. Memory auxiliary Hilbert space HM, which is a memory parallel to this channel, an encoding quantum channel, which takes as an input the system AN and then produces an input for the channel and a quantum memory, and take a specific decoder, which is fed by the input of the Hilbert space of the memory and the output of the channel, and produces a state in the bipartite system VE. Well, what we prove is that there exists such an encoder and decoder in order to have an action which is equivalent to the one that we would have with a random Stein spring dilation. Random means that we don't know what happens in the system E, we just know that it's consistent over all the n copies, and this uncertainty on the system E is just given by action of a random unitary. So, in order to conclude, we have discussed the no-go theorem for purification, how to overcome it with this acorn trick, which is the random purification channel. The random purification channel is an instance of this acorn trick. Some applications and generalizations, also possibility to extend these results to channel. And the main open question is whether we can continue finding new applications of this technique to solve problems or to simplify the approach that we previously knew to relevant questions in quantum information theory. And beyond learning, can we find new application also in quantum Shannon theory or other fields of quantum information theory? So thank you so much for your attention.
Okay, thank you very much for this very wonderful talk. Yeah, it was like very nice to hear, like the first time I heard about it, and then like they have this reduction of this pure state results to the mixed state extension of it to mixed state ones. That was always fascinating to see this. All right, I think we have time, like we have a few minutes for a few questions. So please, if you want to ask something, can you just unmute right now and ask your question? Okay, I don't see anyone at the moment. I'm just sort of like curious. So I guess like this kind of simple construction is enabled by because we have this Haar measure, like you have this kind of like uniform distribution over. But in some sense, I don't really need the uniformity, right? I guess in general. But of course, it can only make things harder, I suppose.
So yes, let me give you an intuition of the role of the Haar measure on this in this setting. Of course, the Haar measure has good properties, and so these natural properties allow for understanding how the channel works. But okay, let me give you a hint of the role of the Haar measure. So here we have an expectation value, and one could wonder, okay, but can we replace the expectation value over the Haar measure with an expectation value over any other measure, any other probability measure? Well, one could wonder, okay, but if I can do it with any probability measure, then I could also take the deterministic probability measure, no? Probability measure which is deterministic on a given UB. But that would mean that here we would have a deterministic purifying channel, and this we know that it's not possible. Okay, so this is non-physical because you see here it's non-linear. So the only linear formulation is this one. A deterministic purification channel, so another instance of a potential probability measure on the matrices, would give a channel which is non-physical. Why your measure is an exception to this? Because it's a uniform measure which gives no information on the purified instance. So it's the maximally uncertain measure on the system B. And this can be understood in the perspective of data processing. When I trace out the system B, so when I move from a pure state on a bipartite system and I trace out a system B, the system B, I'm performing a channel on a bipartite state, so I'm losing information. When I do the random purification channel, I'm doing again a physical transformation. So in general, I'm losing information. I'm not gaining more information on the system B. So the fact that here we have the uniform distribution, so intuitively, it's not a rigorous proof, but means that I'm not gaining information on the system B. So you see this transformation, trace and random purification, they both go in the same direction when you consider data processing inequality, but they compensate for each other. So that's the reason why the Haar measure is fundamental. Of course, if you consider,
I mean, of course, like I'm like, yeah, I definitely want to avoid deterministic one, right? Because I know that's not allowed. But I imagine I was just imagining that what you really need is some distribution that has support everywhere, but it doesn't have to be uniform.
yeah, but then you can take the limit of the distribution which are supported everywhere, but they are
I see,
peaked
I see. Yeah. Like you can
a
sort of like get close to something very peaked, and then that's already bad enough.
yeah, that would not be. What you can prove instead to go in this direction of going beyond the uniform distribution on unitary operators acting on the system B is to consider the symmetries of the system. So if you want to consider random purification only on some states which have particular symmetries, like Gaussianity is a symmetry. So if you take two products, the products of two identical Gaussian states, then if you rotate them in phase space, the coordinate, they are invariant. So this, okay, now I'm being very quick, so it's not maybe clear enough, but symmetries like Gaussianity symmetries or arbitrary symmetries. So I recommend reading this work by Walter and Wittwein. Go in the direction of considering an average over a group, which is not necessarily the unitary group, but a group describing the symmetry of a state and preserving the symmetry of the state. So this is another approach, and this was also crucial in the recent application of purification channel to the connection between learning and cloning, the hardness of these two tasks. they used this idea of preserving the structure while performing this purification operation. So in that case, you don't have they are measured on unitary states or unitary matrices, but you get some other uniform distribution over a group.